Shafi Goldwasser here, who's going to talk to us about the algorithmic benefit of correlated.
Yes, thank you. So a couple of people asked me, what am I doing here? and in fact, I think my talk is a little different than most of the talks in terms of the theme that I've seen. But in any case, okay, so I'm going to talk about something called the algorithmic benefit of correlated instances, and they're actually going to be results from two papers. One that was in ITCS 2015 with Iri Dinur and Rachel Lin, and then a new paper that's going to be in ITCS in a couple months, which we call on the fine-grained complexity of polynomial time problems given correlated instances. So what is this about? So before I actually start, so let me just say sort of in a sentence what this is about. And the idea here is that we also, like I guess a lot of the theme of the workshop, is that we want to try to see what can we do when we have problems which are hard in the worst case. So in this paper, we're talking about problems which are essentially intractable. So let's say NP hard or conjecture to, on the average case, to also be intractable. And in this case, we're going to have problems which are in polynomial time, but that there's strong belief that somehow they're stuck in order n square because of some evidence that has been accumulated in the recent years. And this is in worst case, or even in the average case, at least in the case of this paper. And the question is, okay, so what do you do? So, which has been the theme of this entire conference. But we propose to do the following. That is, the thesis of both of these works and of this talk is that often the problems that you're working with, it's not just one instance that you encounter and that's it, but there's actually many instances, and they're not independent of each other, but they might be correlated in one way or another. And if we could find or get our hands on a bunch of correlated instances, that could be beneficial for us to come up with faster solutions that would break maybe this worst case barrier that we encounter in both of these cases. Okay, so that's the story. And it doesn't come out of sort of thin air, this idea, but really it sort of is linked to something that you see that happens in cryptography. And sort of there is this example that maybe a lot of people have seen, but it's very compelling, so I'll repeat it. And the example is for factoring integers. So that's conjectured to be a hard problem. We don't know how, we have really made no progress in many years on this problem, except for quantum, but we're talking about classical computation. And yet, if you were given a correlated instance, and the correlation here is extremely strong. So this is n, and then there's n prime, which is the product of p, where p is the same prime up there, so n is pq, and n prime is p times q prime. Then once you have both of these numbers, you can find the factorization very easily just by taking a greatest common divisor computation. So it becomes a trivial problem. Now, this seems, a very algebraic, very engineered example. Turns out actually that it was, yeah?
C prime equal to M prime?
Yeah, it's N prime.
C prime? Yes, sorry. This is N prime. Very good. Mike was an MIT student. There's a lot of other people in the audience. No, the reason I say that because now my son, this is being recorded, maybe I shouldn't say that. We'll talk about it afterwards. So there's like this really gift of pattern matching. Like you might perform extremely well in exams, not understanding anything, just from pattern matching. N prime, very good. So,
That's what I'm good.
no, it's a joke. Maybe we can run back the tape. So in any case, this was recently exploited by a paper, actually by Nadia Henninger and other people, where they have noticed, or they saw that in the internet, many keys, actually many composite numbers that people use, let's say if they want to use RSA, in fact are related this way. So they share prime. Or maybe they share, they've used the same pseudo-random number generator in order to choose their primes, so they're shared maybe not such a trivial way, but still a way that can be exploited so you can actually factor the numbers. So you would say that's poor engineering, perhaps, but it's still the case that people do it. And those are the problems that we need to solve. And in general, the cryptographic wisdom, at least, is that you have to beware of cryptography when you're using related keys. So we, at least theoretically speaking, when we write down how you're supposed to choose keys, you're supposed to choose them in an independent way so you don't run into these problems. But the point of today is, I want to say is, the situation might not be so rare, and not just because of some kind of mistake in the way people have selected their keys in the cryptographic arena. And if it is not rare, then we should take advantage of it when we design algorithms. So examples might be, if you're thinking about biology and you want to learn mapping from DNA to, from the genotype to phenotype, and you have multiple organisms, you obviously, apparently in the lab, you study multiple organisms in order to learn from one about the other. But it could be even things that are much more familiar to us, or at least to me. If you think about error correcting codes, it stands to reason that on a disk you have a lot of versions of the same file. And when there are errors, you might take advantage of the fact that you know that these files are related to each other when you correct. Possibly you can correct for more errors if you assume that about your data. And in learning, I know that people have looked at examples which are correlated. You could even think about concepts which are correlated to each other. So to generalize all of this, we'll say that whenever the instances are derived from one source, and then of course we have to explain what this source is, but intuitively, let's say they're derived from one source, then we should treat them as correlated and try to solve them together rather than separately. Now, since the whole theme of the workshop is that we want to talk about real data, then that might be the case. That in approaching the problems that you're approaching, one takes advantage of the fact that the instances are related to each other. And pictorially, we think of a source. There are these instances. We design algorithms that work on one instance even individually, one at a time. And the suggestion is, and I'll try to convince you in this talk, is that this suggestion works, at least in the theoretical examples that we came up with. The suggestion is that instead of working on one instance on its own, you should design an algorithm which takes all these instances together and comes up with a solution. So again, the algorithm is not, yeah.
So what we do in machine learning is not work on them simultaneously, but work on them subsequently, one after the other, but eventually improve as the algorithm gains more and more knowledge from the previous example.
So the thing is that that's actually not a bad point in order to explain that that's not what I'm doing. So in other words, in machine learning, do I understand that at least when you're training, right, you're given solved examples. So you're given labeled examples, and this improves, and this enables you to come up with a good learning algorithm.
No, I'm talking about related tasks that you say for driving. You have different tasks, but you start with the first one is very difficult, and then the second one is kind of correlated, and it's become a little bit easier if you base it on the algorithm that you got for the first one. And then you keep improving with new tasks, not with new examples.
Okay. So, but I do want to emphasize in the context of this talk that when we get these instances, or if we want to think of them as examples which are labeled, they're actually not labeled. So we've got a whole bunch of instances. We don't know solution to any one of them, okay? Or we know that somehow they come from the same source. So let's be a little bit more formal. So I want to think of a model. There is some sort of generating process, and we want to think in this generating process, there's something we call a primary instance. And the primary instance, let's say, might be a worst case instance that I want to solve. And it has some underlying solution. It might have many underlying solutions. Let's call S a specific solution. So we have an instance and a solution. And it could be an average case instance, a worst case instance. Let's say that that's what I care about. We will say that there are also auxiliary instances, okay, generated by this generating process. And they are correlated to the primary instance. How are they correlated? Depends on the problem, but let's think of it this way, that these auxiliary instances, they're I1 through In, and they also have hidden solutions S1 through Sn, and these are distributed according to some auxiliary distribution that depends on both the primary solution and the primary instance and solution. So in other words, I don't want to be the case that you have an instance, okay, and then you perturb it and you get a whole bunch of other instances. In a sense, the intuition is that you have an instance, that instance has some solution, okay, and the auxiliary instances are such that their solutions may be correlated to the solution of your primary one. But, this is a general framework. All I'm saying here is that this distribution depends on both S and I. Okay, so in both S and the specific, on both the instance and the specific solution.
So the solution being correlated.
Yes.
By correlated, I assume you mean like common bits or whatever.
It's up. Well,
No.
Great question. Because my next point is that's the $1 million question. What kind of correlation to consider? So this one I didn't say. I said the word correlated, which means what? It means Formally just means that it's selected according to a distribution that depends on both S and I. I didn't tell you how, and that will be actually problem specific. Because in a sense, it must be. Okay, why do I say that? Yeah.
Maybe I'm repeating the question, but why isn't number one just some string of bits?
Which number one?
Well, in the previous slide, you had 1 and 2.
It could be
A string of bits, and then you have i's and s's that are.
I don't understand what you mean by one. So one.
Number one is I and S. Number two is I1, I2, and why did you use I and S for the first point, not just a string of bits? Because
You don't see S.
You don't see S. The input is I. That's the instance. So it could be a graph, it could be a number you're trying to factor, it could be a set of equations you want to satisfy, okay? What would be a solution in the graph case? If you're thinking about the clique problem, it would be some clique, okay? If you're thinking in the factorization number, it will be the factorization. And if you're thinking about a bunch of solutions, it might be a satisfying assignment to these solutions. Okay, so I's are our usual instances. And we are looking to solve a problem. Okay, and S corresponds to a solution. Is that okay? Okay, so now let's go back to this question. What kind of correlation are we talking about? It will become much clearer when I start talking concretely, okay? So what kind of correlations do we want to consider? Again, we're staying in the high level. We still didn't talk about an example. But I want to say that there's sort of 4 kind of rules of thumb behind what correlation models are reasonable, okay? Because you could say that you could sort of trivialize the problem if you don't choose the correlation in a meaningful way. So specifically, I want to make sure that these auxiliary instances that are being generated for you will be hard to generate given the primary instance alone. Because otherwise, just take your instance. If you could take your instance and you can generate these things on your own, there's nothing that they're giving, there's no point in getting them from the outside source, okay? Good. And hard here means the complexity of solving a single instance should be hard to do it within that complexity. Okay. Secondly, you don't want to consider a model where you're given so many auxiliary instances that your size of your input has got to be so large now that the whole thing got trivialized. Okay. Thirdly, you don't want the solution to your hard original primary instance to be trivial to derive from the solutions to easy auxiliary instances. So think about auxiliary instances where essentially the new instance has a solution written in it, a solution for the primary. I mean, that's kind of stupid, right? So again, we don't want it to be a trivial extraction of solution from this auxiliary stuff. And most importantly, which is the hardest part, is that somehow we hope that this is this access to these auxiliary instances is some approximation of reality. It's very vague, right? So in other words, I'm saying there is some process. The generated, let's just think concretely, graphs. There's some process that generated your graph, okay? And then there's other graphs. And we're going to say we're looking for 3 coloring of this graph. So we would want that these other graphs, their 3 colorings, okay, if they have them, are correlated to the 3 coloring of the original one. Okay? How correlated? Well, if there was some process that generated this graph, somehow you want to say that this process emulates some natural phenomena. Yeah.
So just to connect to our previous discussion, so this is kind of like a setting where the solutions do have semantic meaning. So the I sub j's, they're not just a function of I. Really, the solution means something. So it's not like you just took the I.
So the I was the instance.
Yeah.
I my subject. Okay.
Right. So the new instances aren't just a function of the I. The
No. They're
They're
actually.
the solution too.
That's right.
So there's some meaning there in the solution. It should have some.
Yeah, absolutely.
some
So that was
semantic
very
meaning.
important. That it's a function of both S and I. Okay. All right. So let's look at some examples where this kind of methodology actually gives you great benefit. And you will have to be the judges whether the correlation that we assume, because we have a theoretical treatment, is reasonable or not. Okay, but the methodology still stands. Okay, so I think it is important to consider what else is available to you except the problem at hand. Okay, so so I said that there are two papers that I'm going to talk about. First one talks about constraint satisfaction problems. So this is a very rich class of problems, captures a wide variety of problems such as K-sat, maximum cut, 3 coloring, systems of equations, and so forth. So constraint satisfaction problems essentially capture almost all local problems, or problems that are essentially the task is to solve a whole bunch of local constraints. It's NP hard. Okay, in general, to do CSPs is NP hard, even to approximate them. It's conjectured to be hard on the average. There's several, conjectures in the literature. There's this thing called Goldwasser one-way function proposal, which is based on constraint satisfaction problems.
So by the way,
Yeah.
there's two separate things. There's CSP and there's max CSP, right?
So
Like
I'll tell you
max
exactly what I mean by CSP, okay? You're right. So what do I mean exactly by CSP? Here's a definition. So I'm going to restrict myself to talking about these kind of CSPs. So first of all, there's a P, which is a predicate. And this is a function essentially that goes from D variables to 0, 1. So it's a Boolean function. D here, you think of it as a constant, okay? So it takes D bits and tells you 0, 1. And I want to think now of, in addition to P, there's a graph, okay? The graph is a graph that connects, it's a bipartite graph. It connects sort of inputs to outputs. So you can think of the inputs as sort of the nodes on this graph, which are labeled, let's say by 0, 1. And then at every, if these three nodes are connected to this guy, then we label it by applying this predicate on the labels of the inputs connected to it. Okay? So the constraints are, okay, so if you're given essentially now only the output bits, and let's say you're given 0, 1, 1, 0, and so forth, this is specifying constraints on the input variables. So they have to be such that for this to be 0, those three variables under the predicate will give you 0. So these are the constraint satisfaction. Often, regardless of whether it's max or not, people think about all constraints being satisfied. Namely, let's say all ones. But that's not a big difference because we have negation, so that's the same. The thing is, going back to your max question, is that the problem that we prove is hard is to maximize as many as possible. Where here we're going to restrict ourselves to those instances where we know that they all can be satisfied. Okay, and that is a restriction. And the results I'm going to describe are for those cases. They still seem hard and have been conjectured hard. And that's what this Goldwasser one-way function is given a function that's described this way, okay, try to invert it. Doesn't seem to be much easier or any easier. I think there are some predicates which are not good for it, but essentially almost all predicates, we don't know anything better than general CSP. But it is an interesting question to extend these results, let's say, to a problem where only 99% of these constraints should be satisfied. Okay, but did I address your question? Okay, so we are restricting ourselves to those class of CSPs where we do know that they all can be satisfied. Okay.
And then my question came because in your examples it was max cut, which
yes,
really
that's
doesn't
true.
make sense without
That's
the
true.
maximum.
That's true. I should change that. Okay, so what's an instance in this case? Remember I talked about instance and solutions. An instance is essentially a pair of a graph, so that kind of tells you which x's go to which y's, and a particular y. What's y? It's an output labeling. So I have an output of the labeling. I know what the graphs are, what the graph is. I know even what the predicate is. And all I want to find out is the x. Okay, that's my solution. So x is a solution, and this is the instance. Okay. So are these hard or not? As I said, it's conjectured to be hard on the average. And the parameters here are, let's say, the d, the little d, how many x's go per y, the density, which is the ratio between the number of output bits and input bits, the predicate. And that's going to be the problem in the sense that is hard today, but with correlated instances is going to become easy. So by using extra correlation, extra instances, which I will describe in a minute, you can make this problem, you can have polynomial time solutions for this problem. Good. So what are the correlations? Okay, so this is kind of the interesting question, are these reasonable models or not? First, so the first is what we call a randomly perturbed correlations, or in the model is the following. Choose your primary instance, just like before. It has the graph, it has the solution, and it has the graph, it has the y, and has some hidden x. X is what we call the solution of this instance. And auxiliary instances are defined as follows. Take the solution x to the original primary guy, so the labels on x, and perturb them. So how do you perturb them? Just take every bit and you flip it with probability epsilon from 1 to 0 or 0 to 1. And now, you sort of plug in this new x and you get a new y. So this is, each one of these is generated exactly this way. Each time a new perturbation of the x gives you a new instance.
Sorry, what is y?
Yeah, y is, remember in that graph, y is the labeling on the output bits. And x is the labeling on the input bits. So I'm given y and I'm wondering which x made y happen. Okay. All right. So this is this random perturbation model. Another model is the following. So in the algorithmic problem is just as usual. I'm given the gy, gy1, gy2, gy whatever, and I'm looking for x. I'm not given the x's. Another model that one considers is, yeah.
So just to understand, if you had clauses, right?
Yeah.
You're not changing the clauses. You're only changing whether they are 1 or 0.
I'm changing the variables, not the clauses.
Yeah.
So the clauses are the same. So it's the same. You're asking me it's the same graph each time.
Change
Yes.
the solution, and therefore these 1 might become 0.
That's right. That's right. That's right. I'm not changing the predicate. You can actually have different predicates on each bit. That's not going to make a difference. Same results, but the graph we're not changing. It would be more general if you had different graphs for each instance. Okay. So the second model is the following: is the same, except in addition to being given these gy1, gy2, gy3, and so forth, somebody is very considerate of you and gives you also the differences between x and x1, x and x2, x and x3. So in other words, there's an x that causes a y. Then there's an x1 causes a y1, and x2 causes a y2. You are looking for x, and somebody tells you, you know what, I'm not going to tell you what x is or what x is, 1 is, and so forth, but I'll tell you the difference between x and x1, x and x2, and so forth. It seems like a lot, okay? In fact, it is extremely useful. But I want to say that, in my opinion, it's natural as well. Why is it natural? Again, thinking as a cryptographer, then often we can tamper. Okay, so we have a key. We don't know what it is, but possibly we have the ability to tamper, let's say, to go to a bit and flip it. To go another bit and flip it, okay? And ask, now what? Does the problem become any easier? What I'm doing here is not that. I'm not allowing you to tamper. I'm not allowing you to say that you would like to take x and get a specific x1, which is a tampering of x. All I'm saying is if somebody randomly changed x, they will tell you where the changes were made. But they're not telling you if it went from 1 to 0 or 0 to 1. Okay? Yeah.
Should I think of epsilon as a constant or like subconstant?
Let's just think of it as a constant.
So like even half?
Yeah, from 0 to half, between 0 and half, yeah. Now the thing about this model, I don't think it's that impossible to think that we know such, that we would know that for something that comes up in nature or naturally. But in any case, the reason why we introduced it is because it's a stepping stone to get the results. So we will first solve it in this model, and then we'll show how to approximate this model even in this case. So the way the algorithms will work is that they, in some sense, will approximate the differences, and then using the differences, we'll be able to solve the original x. Okay, so what are the results? So the first result is that given random primary instance, so even the original one was a random primary instance, and auxiliary instances which are randomly perturbed, the way I described, there is an algorithm that finds a solution that satisfies almost all of the constraints. So you can do this in polynomial time. Now, you're not going to find the original necessarily all of x, but you'll find something which is close to x. So when I say satisfies almost all of the constraints, x prime can be shown to be close in Hamming distance to x. I'm sort of going to go faster because I think the second half is actually much more interesting, but I want to still say what we can get, okay? And I see that it's almost already 4. Question?
It's interesting that you get almost all of them.
Yeah, you would think you could get all of them,
Yeah.
So
but
there
it's not
could
trivial.
be many solutions, so I guess X is sort of unique.
X is not unique, you're right, not necessarily, but one can show that the thing that you'll find will be close to that x. Yeah. And I'll talk about how in a minute. What if your primary instance was worst case? Okay, so it turns out that if it was worst case, and you consider the second model, the one where not only that it's a perturbation, but somebody even tells you the differences between x and x1, x and x2, x and x3, then you can actually find x prime that satisfies all, so not just most, okay? And furthermore, you can do it for a worst case. So in some sense, you've made your life easier, right, by giving these known differences for the algorithm. You've made it hard by making it work on a worst case instance, but the making easier was help more than the making hard, and you can solve for a worst case instance. Okay. This constraint satisfaction problem. It's actually sort of more general than what I'm saying. It doesn't, D in everything I was saying was a constant. So like in the picture, there were 3 x's going to a y, but you can extend this actually, to locality like order log n, and it's tight. So you can also show that there are predicates with some arity C log n, which are NP hard. So it's below log n. Okay.
Does your result change if you change the definition of how you define differences between x and xi? Like, what is your measure of distance between them?
My measure is Hamming distance. Yeah.
But if you were to change that, would that change your result?
Well, I don't think I have a result. I mean, the result is for Hamming distance. Okay, so it's not a general result. It's a good question in the context of the next talk. In the next half of my talk, that will come up. And the third thing that I want to say is that how many extra instances did we need in these 2 theorems? Order log n. What if you had only one single instance, an auxiliary instance? So you had your constraint satisfaction problem. Somebody gave you a perturbed version, another instance. It turns out even there you can do something. You can find a solution, but that's only for a restricted class of P's, of predicates. So it's the kind, you remember predicate was, I was taking x1, x3, and x7 and doing a predicate on it. When these predicates are sort of highly correlated with one of their inputs, okay, so P of x1, x2, x3, I think it's always x1, or highly correlated to x1, then you can actually solve the problem if you only got one extra instance.
Sorry, do you know that log n is tight, or it might be the case that some other smaller amount is still enough for the result?
No, I don't know it's tight. Could be. Could be 1. Okay. So what's the idea? Before we go, I just give you like a 2-minute idea. So what's the idea? So the idea is the following. So let's say that we have a particular input. So it's a particular graph, a particular y, a particular predicate, okay? And we want to find x. So let's think about it. What's happening here? So this is, let's say, the original x, okay? And we don't know what it is. That's what we're trying to figure out. This is the y's. And then somebody also gives me a y1, a y2, and so forth. This is essentially a y1, which is obtained by perturbing x, doing the graph, doing the predicate, okay? So and let's say we're in this, just to give you the idea, we even know the differences. So we know the deltas between x and x1, x and x2, and so forth. So what does that mean? It means that if you sort of restrict yourself on a particular bit location, we're trying to figure out what the x's are, right? Let's look at a particular bit location in the output. So this is the this bit location in y, in y1, in y2, and so forth. We know that this bit location is the result of applying the predicate on 3 bits, which we're trying to figure out. And similarly, this guy is the result of applying the predicate on 3 bits we're trying to figure out. So what you can observe, that since we've taken order log n instances, that it's easy to see that eventually that we will actually see all possible differences. So in particular, we'll see all possible 3 differences for this bit location. And that suggests that we could think of another encoding for x. So I'm trying to figure out what x is, okay? What do I know now? So here's a new encoding for x. Essentially, it's the value of the predicate, which I get because that's the y, and x plus a shift. And I get this for lots of shifts. And if I get it for all shifts, this is an alternative, essentially, encoding of x, which I can, which means that if it was unique, I could figure out what x is. Why? I just enumerated all possibilities. How many bits are we talking about here? D? That's 2 to the d, it's no problem. Great. So, but who says it will be unique? It doesn't necessarily have to be unique. So this encoding doesn't necessarily pin x down.
So for 3 stat, that would be easy. It's like trying to work. Or would be good.
Right. That's right. That's right. For some predicate, as I said, it's not unique. But you can show a lemma that's essentially that for all predicate, regardless of what it is, there is some unique linear subspace which will contain all the differences between x and x prime, as long as x and x prime have the same, essentially are encoded, their encoding is the same. So what that means, what?
So if it's not unique, doesn't matter which one you find, right? You can find any one of the x's.
No, the problem is that I need to paste all of them together.
Right.
So this is what find those 3 bits and those 3 bits, but it has to be consistent. Okay.
System of
What?
So we'll get a system of equations.
Exactly. So we can write down a system of linear equations and solve them. Okay, and that's the algorithm. Now, what if you wanted to address the case where I didn't know the differences? This kind of heavily dependent on the differences. The strategy will be that we want to approximate these differences. How do we approximate them? Well, what we know now, just sort of in a word, what we know now, if we get back to this picture, okay, now I don't know the difference. But what I do know is that if this flipped, let's say if it went from 0 to 1, it must be that one of these 3 bits flipped. I don't know which. But again, given enough like order log n instances, I'll do some voting, and I'll be able to get some an idea. It's not so simple because you get these noisy linear equations at the end, because even this idea is just a guess, and you have to solve a system of linear equations. But it's okay. We'll deal with it somehow. All right. So I think that's all I want to say about this paper. Let's just do quick reflections before we get to the next one. One thing one may say, as they say, the adversary, that maybe this whole thing worked because this was a randomized CSP. The theorem that I did, theorem 1. Maybe when you talk about average hardness, CSP is not hard, but that's probably not correct because you can actually get correlation didn't help you just because of that, because essentially you can take a PCP instance of something NP hard and kind of encode it this way and still show that it will succumb to correlation. So it's not the inherent easiness of what we started with. The second thing is that you could talk about is how much correlation do you actually need? And it's sort of non-monotonic, because if they were completely correlated, so all the x's were the completely correlated, that's useless. Because the same problem, I can repeat it as much as I like, it's not going to help me. So there is some combination here of that they have to be correlated, but not too much for sort of the sweet spot for this to work. And it's sort of an interesting question to study where that happens. But maybe the most interesting question, which will lead us to the next paper, is, okay, CSPs, these intractable problems, who's going to give me these correlated instances? Well, I don't know, maybe they will, but let's think of something a bit more natural. So in particular, how about problems in P? So what we showed is to take an intractable problem, whether we prove it's NP complete or we just don't know the solution, make it tractable. But how about problems that we actually solve all the time in polynomial time? Is there any benefit to this idea of correlated instances? And if so, which one should we look at? So the idea is that we want to, of course, look at polynomial time problems where we have some confidence in the fact that we've sort of reached the best of our abilities and try to improve there. So the place that we're going to look at are these problems that come, so let me tell you which problems, okay? So I'll enumerate 3 problems and then explain why we chose those. So the first problem is going to be the longest common subsequence problem. So here you're getting 2 strings, okay, over some alphabet, and you're asking what is the longest subsequence, which is not consecutive necessarily, which is common to both, okay? The second is the edit distance. You've gotten 2 strings. You know x and y. You know that there's a way to go from x and y by inserts, deletes, and change of characters, and you'd like to know what is the minimum number of these edits, okay, maybe to find them even. That's the edit problem. So this is a max problem, this is a min problem. I gave examples here, but you all know, what this means. And the third one, sorry, there's 4. You can think of longest common subsequence, not just 2 strings, but k strings, okay? Sometimes people call this multiple sequence alignment. The last one is something called dynamic time warping distance, and the idea is the following. Again, let's think of it as if you have 2 strings, just like in the longest common subsequence. But now, when you're traversing them, okay, you're walking in this one and you're walking in that one, you want to traverse them possibly in different speeds. So you might go, you have a finger here and a finger here, and you might go faster on the top one than in the bottom. And what you're looking for is the minimum number of mismatches in a traversal, where at each step either one or both strings moves forward. So you're sort of making steps going forward, and you're looking to see when you're going to get a mismatch. Okay, so this is essentially a very natural measure. I don't want to get too much into it, but it's a very natural measure when you are sort of comparing two videos and you want to know if they're the same, one is in a faster speed than the other, or audio. What's true about all of these things are that they're all sort of similarity measures between strings, okay? And what's true about all these similarity measures is that they sort of depend on the size of the set of matching pairs. So if you think about matching pairs, like A and A here and A here, that's a pair, or B and B here, that's a pair. And the number of matching pairs will kind of dominate the complexity, or sort of will be a crucial part of the complexity of solving these problems.
And the number of the matching pairs in the problem, or in the specific pair of instances?
In the specific pair of instances. But again, this is just, if people are interested, can look at the paper. There's a way to generalize all of these measures that I talked about in something called a similarity measure, and the algorithm that I'll describe works for anything that obeys this generalization. So what's known? Okay, so we know for these problems, for all of these problems, we know that dynamic programming, is the solution, order n squared, right? You try, good. But what's interesting, and why we chose this, is that we know that any improvement, let's say to get to n squared minus, if we shave anything up here, will imply that there's a whole bunch of other problems which will be improved. This is this fine-grained complexity theory, where they show equivalence, these fine-grained equivalences between problems, that if any one of them you can beat the rest. We also know that if you can beat it, it contradicts some sort of complexity assumption. I don't know what to make of that, but it is what it is. And the next thing that I want to say that we know is that you can find these examples, in contrast maybe with the constraint satisfaction example that I gave, which was a sort of a one-way function construct of cryptographers, in the real world. So longest common subsequence or multiple sequence alliance is really what they do when they align DNA sequences, sort of in evolutionary studies. So these are natural problems. So again, remember, our whole thing was that we wanted to find natural problems where we can get lots of instances which are correlated to each other. At least these are natural. And now the question is, can we take advantage of the correlations to solve these problems? Okay? So what correlations? I haven't said. These are going to be different than what we did in the previous part of the talk. So here's the model. There are going to be two models I'll talk about. One of them, am I out of time? No. Well,
We started late.
okay. So one of them is the following. And this is a very strict model, and then we will relax it. So here the idea is this. The primary instance, and let's just look at longest common subsequence. You can essentially see what it would mean for the other models. So for longest common subsequence, we have a pair of strings. That's my primary instance, right? And let's say the solution, I wrote I here, should be S, but in any case, what is the solution? The solution would be the location of the longest common subsequence to X and Y, right? The auxiliary instances are going to be defined as follows. Take a random pair, X1 and Y1. Okay, so these are random strings, have nothing to do with your original XY, except for the following, which is what you'll force, and that is, let's say that if you look at the locations where the longest common subsequence was in X and Y, those locations in X1, Y1 also have matching strings. So here, so let's say if this is X and this is Y, let's say that B, B, A, B, it matches here. This is the longest common subsequence, okay? Then in that location, the second, the third, the fourth, and the fifth will match exactly what's in the first, second, third, and sixth, okay? And that's true for this pair of instances, for this pair, for this pair. So these are this is my auxiliary instance. X1, Y1, X2, Y2, X3, Y3, and so forth, okay? Notice that it's not the same string, these are different strings, it's just that the locations are. So one thing to notice is that the fact that it's not the case that these locations are also the longest common substrings for these instances. So they have matches in those, but if you solve the longest common subsequence on this, it doesn't give you the longest common subsequence over here.
Can you, you here you were trying to look from natural problems.
Right.
Is this type of correlation, does it appear in the nature, in reality?
Let me get to that in a minute, okay? But because I want to first relax it. Yeah?
So how do you generate such pairs? Do you fix X to be a random string and then you make Y to satisfy this property? Or?
That's a beautiful question. We don't generate them. Because if I could generate them, the whole point of this, and thank you for the question, because I think probably half the audience is under this misunderstanding. I get it from God or whatever you like, Trump. No, I get it from some supreme authority. Okay, there is this x, y that I want to solve. Okay, somehow I can also find these extras with this promise. The reason I wrote it the reason I wrote generate is because I want to have a formal definition of the generating process. There is some process that generated this way. Now they only give me the x ones. Okay. All right. And what's a relaxed one? A relaxed one is essentially the same, except now I don't force those equalities. I just want that the locations where the longest common subsequence appears in x and y will contain a match in the auxiliary ones with probability better than random. So whereas if you think here, it was really A went to A, B to B, and so forth. In the relaxed one, these strings are more there is a higher chance of being A than B, more than 50 plus epsilon. Okay? So there is some reason, there is some correlation, but I'm not forcing equality. Okay, so now you asked a very good question. Does this come up? That is where I can prove the results. Okay? It is, no. I mean, I think we should all be honest, okay? And I don't think it's unlikely that you can get, let's say, DNA sequences that have some correlation. Is it exactly this? Is it in the neighborhood of that? I don't know. In fact, let's put it this way. There's theorists and there's practitioners, right? And whenever you talk to theorists, they say, you require too much. There's never such sequences. So I actually went and talked to a whole bunch of people in the Broad, described it to them. They said, you know what, let's try it. So they are not so negative. Do they know their data? Better than we do. So in order to answer that, I think you have to run it on real data and see. Probably it's not exactly this model. This doesn't mean that the algorithmic approach that I'm going to show in a minute will not make some kind of a dent in the data they do have.
You're saying they were hopeful for this,
This is the paper I described.
No, the subsequencing. Which one was it?
The subsequencing.
The subsequencing.
A multiple one, which is going to be same complexity improvement, which I haven't said what it is yet. Okay, so the improvement is going to be the following. We're going to show subquadratic algorithms. We're going to beat this order n squared. Okay? And how many auxiliary instances? Order log n. Okay? So let's just give you the idea, and then we'll be done, I think. So the main theorem, just to be more explicit, is that you can get order n log n for the strict model, where I'm forcing the equality, and order n to the 1 plus d, where d is less than 1, so we're beating the n squared in the more relaxed model.
And the relaxed model was what?
The relaxed model is where I don't force equality in the auxiliary strings, but just they are more likely half plus epsilon of equality. Okay.
Can you do half plus epsilon? Can you do 1 over sigma size plus epsilon? And 1 over the alphabet size plus epsilon?
Yeah, the alphabet is just constant.
But right now it's 2, but it's half plus epsilon. But if you had a four-letter alphabet, could you do 1 quarter?
Yeah, that's fine. It's for general alphabet. I didn't say 2.
No, but can you tolerate 1 quarter plus epsilon?
Yes. This has nothing to do with it. So it will equal it. So the way that I do it, I say toss a coin, bias half plus epsilon. If it comes up heads, I make it the same. If it comes up tails, I make it anything else in the alphabet.
Right, but I'm saying that there's already information if you make it agree more than quarter of the time.
Yeah.
Is already more than random.
Much better.
So can you do 1 quarter plus epsilon?
No. I mean, I have to think about it. But I have to think about how the probabilistic analysis works. It's not a very deep one, so it's an easy calculation, but I'd rather do it offline. But I don't think so. But it's not something that I actually tried. Okay, so what's the idea? So here's the algorithm. So let's say we have a primary x and a y, okay? And the length here of the string is 6, right? N is 6. And the auxiliary, let's say, are these pairs. Pair, 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 pair. So the first thing we do is the following. The main idea is that we're going to define a new longest common subsequence problem with a different alphabet. Okay, what is a different alphabet? So I'm going to consider the following vectors of characters. So let's take the first position, okay, in x. So this is in the x and in all the auxiliary x's. So this is A, B, A, B, A. That's the first position of the x's. Okay, so I'm taking essentially all the first characters and all the x's. And that's my first vector. Okay, then I'll take the second position. You know, B, A, B, B. So essentially, for each position in the string, the first, the second, the third, up to the end, I make these vectors which we can think of as essentially new characters in an extended string. What's the extended string? This is its first letter, this is the second letter, its third letter, and so forth. I do this for the x's and I do this for the y's. So now I have a new instance. It has this bigger alphabet for character 1, character 2, and so forth. Now notice the following, that if you look at matches, okay, just for the example I did, I didn't explain why, but in a minute it will be clear. So if you look for matches now, by matches I mean before an A and an A anywhere, that's a match of a pair. Or a B and a B anywhere, that's a match. So the same way here, a match means a character here which is equal to a character down here. These are exactly going to be the matches. So I think I have this guy goes to here, they're the same, right? So there's B, A, A, B, 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 A, A, B, B, and so forth. The matches actually occur exactly where the longest common subsequence was. So it's like the second, third, fourth, and fifth in the first, in the X, and 1, 2, 3, and 6 in the Y. Y, that is WHY. It's not a coincidence, obviously. The reason is because when you have order log n auxiliary instances, the probability that anything not in the longest common subsequent results in a matching pair in this extended string is low. So by doing what we've done, okay, we've made it that if there is a match at all between the extended X and the extended Y, it's going to occur in something that was in the longest common subsequence. Which means algorithmically that all we need to do now is not solve fancy longest common subsequence, we just have to find matches. So because the intuition is, if you found a match, it's part of the longest common sequence. So just look for matches. By matches, I mean if you just thought about the ordinary strings, an A and an A meeting each other. Except in this new alphabet, that's all. If it does happen, they're already part of the longest common subsequence. Okay, so the strategy is to find these match vectors in the top and the bottom. And how do you do it? You use hashing. What kind of hashing? Well, if you think about it, I could take everything that's in X and just hash them, and I do it for the guys in Y, and they will fall into the same bucket. And that's why it's n log n, because I'm hashing n of these vectors, right? Or as many vectors as locations in the original character. Each one of them is log n long. Okay. What about the relaxed model? Okay, and then we'll be done. Will this work for the relaxed model? No. Because in the relaxed model, the pairs of the longest common subsequence are only guaranteed to match with higher probability than the others, but not more than that. So essentially, the idea of a match doesn't even exist anymore. They're not guaranteed to be the same, but there is some guarantee. So if you look at the vectors up and the vectors down, okay, in the location where there was the longest common subsequence, then they will be closer together. So you look at those two vectors, they're going to be different. But they're going to, right, so in the top and the bottom, but they will be sort of closer than if they were just chosen completely at random. So this suggests that the thing is to try to find essentially close or neighbors. So we want to essentially run an algorithm which will allow me to show which vectors are closer to each other. And in fact, in this sort of Hamming distance, in which dimension, well, log n, right? Because I had log n instances, and each character in the alphabet had log n coordinates into it, okay? And I just want to now take one of these extended characters in X and look at who's closest to it in the Y's. And the one that's closest to it will be essentially the guy, which will be what I correspond, my guess at a match in the longest common subsequence in the primary X and Y. So essentially, we use an algorithm. There's some recent algorithm that we use, which achieves this running time. And notice what's going on here, okay? And in fact, so we are shaving off, it's not n squared anymore. Their algorithm works for, it finds nearest neighbors whenever the dimension is order log n, which is exactly our case. And we're done. So obviously in the relaxed model, we're taking more time. This is not n log n, but it still beats the quadratic bound.
Question?
Yes.
So in the exact model, what was the algorithm?
In the exact model, it was I was looking for matching characters, and the way I'll do it is by hashing.
By hashing.
That's all. Okay. So I just want to say a word. I thought Robbie was going to be here, but he's not. Is that there is another model. It's not the only thing. We have some other correlation model for edits. So what would be a natural thing for edits? Forget everything I said so far. So for edits, a natural thing for edits would be is that you say x and y, then x prime and y prime, they use the same edit sequence. So if they go from x to y, you have to delete the third character, insert a seventh, you change a whole bunch of things. You do the same to an x prime. An arbitrary x prime, you do the same, okay? So one can show order n log n for this correlation model, and it's very related to some work. It's very related, not in technique or anything else, but there is a work on smooth analysis for edit by Robbie Kartmar and Andoni, where they were trying to figure out if there's something they can say about the edit problem which is better than order n squared. So what they said is, we want to think of smooth analysis. Now what they meant by smooth analysis is the following. They said, let's take an x and a y, whose longest comes, and let's think about where their longest common subsequence is, okay? And now we will perturb, because it's smooth analysis, we will perturb x and y at will, okay? Except for where the longest common subsequence is, we do the same, with the same changes. So if there was an A and a C, they both turn into a B, okay? And then they say this is sort of smooth, or at least it's a perturbation of the original one. And they show that, in fact, for this model, they can come up with a linear time approximation for minimum edit, okay? So what is the similarity? It's completely different. They're perturbing something. We are given an instance, okay? Also, their perturbation is not something they can really do, because how do they know where the longest common subsequence is? So it's also a little bit in this realm of magic, except they're not getting additional correlated instances. But where I see the similarity is that it's interesting that the same model came up. Their perturbation model was the same model that we essentially use here for correlation. That's, to be interpreted. So there's lots of open problems, I think the main problem is whether, for example, what we've done has any bearing on real sequences. Or find other correlations in nature where the speedups can be obtained and rigorously analyzed. What else? So I guess I conclude that I believe that correlated instances are available. It's really for us to take advantage of them. So the challenge is, how do you take advantage of them? How do you define them formally? And possibly, as was the theme a little bit in this workshop, as I understand it, maybe the only way that we'll know what correlations are out there is to try these algorithms. But I don't know if I got the right takeaway message. That was one. Thank you. Yeah.
So the reason for n squared in LCS is basically, you have a dynamic program and you have this matrix that you have to fill up. So can somehow generalize what you've done to maybe some sort of dynamic program type approach, where you say that you don't have to fill the entire dynamic programming table, you just have to find some small part of it if you get lots of correlated instances?
So I'm not sure this is what you mean, but it has occurred to me that one way to get correlated instances is in any dynamic programming algorithm. So if you think about dynamic programming, right? I've got some local function. And the way we do it is we already solved the previous ones, now we're going to solve the new one. So in some sense what this is saying, maybe instead of solving them, you take the whole neighborhood and you solve it together, because you know that you even know what the correlation is between them, because you are the one, that's how you define your problem. So I don't know if that's what you're getting at. But I don't see as it is now, as dynamic programming at all. Yeah.
So is there a way, in reality, you may not know if your instances are correlated or not. Is there any way of checking? If I get a sequence of instances and I want to know which of them are correlated, because then I'll solve them together. But is there a way of checking if they are correlated without actually solving the problem?
Well, in the factoring example, you do know the correlation, and you do know they're correlated. You may know because you may assume that there's a limited amount of randomness in the world, or everybody's using the same source of randomness, and that's how your instances were generated.
Let's say in the edit instance, I have two instances I want to know.
So
can I solve them together?
So even in evolutionary studies, they have all kinds of models of how evolution proceeds, and are they correct? I think in a sense, if you run an algorithm and it works, gives you some evidence. It's a good question. I don't know. Yeah.
Well, directly related to that, there are mathematically tractable simple sequence evolution models, right? like the Kimura model, for example, which is extremely simple probabilistic. So for those, would you get correlated instances if you presume that?
I think you would, and it would be the right thing to do is to analyze.
So that would be really interesting, because then you should be able to solve multiple sequence alignment problems in better time than pairwise sequence alignment, which would be wonderful.
So by the way, the multiple sequence alignment, according to this model, will get you order a k n log n, which is much better than what they do, which is n to the k.
Well, exactly.
But it's this model. So I'm saying it would be the right thing to do going forward is to take one of these models and try to see if we can, the correlations that have been defined there lead to a better algorithm.
Exactly.
Right. No, of course. Yeah.
So it seems like this model is asymmetric in that there is a primary instance and all auxiliary instances are perturbations of that primary instance. But then if I were to pick an auxiliary instance and call that the primary instance, the others are not.
That's great. So that's
I would expect.
So that's another correlation model which one could analyze. We didn't do it, but I think that's a great open direction, even in the CSP. So the suggestion here is rather than x related to x1, x related to x2, x related to x3, you take x, you perturb it to get x1, you take x1, you perturb it to get x2, and so forth. So if you think evolutionary, let's say these things progress in time or something. I agree with you. That's a different model, and then you have to get different algorithms.
I have one more point. I guess if you were able to measure the correlation between problem instances, like Shai said, I guess it wouldn't be the original problem. By itself may not be hard, because then you might be yourself able to generate instances that are correlated with the current problem, and you might be able to solve it as you.
Just because you can verify doesn't mean that you can generate. He was just saying that whether you can verify given data, whether a certain model correlation is true. Yeah.
So, especially the relaxed model, can you get any approximation in better time? Because I think the edit distance, actually there is no better than polylogarithmic approximation in less than.
So you're saying rather than going for exact and get it to, and be satisfied with the n plus 1 plus d, try to get an approximation in linear time, say.
Exactly.
We didn't try. That's a good question. Yeah.
One more related to the CSP work. You assume that the graph remains fixed, right, in your correlation model.
Yeah,
What happens if you actually allow little perturbations in the graph as well?
I think it was important for the analysis that the graphs are the same graph, but
it seems to be crucial for your algorithm, but you might still be able to do something if you can bound somehow the amount of difference in the graph.
That's right. So we would just looked at either all the same or completely arbitrary graphs, but if they're related, obviously you can get something, right?
Yes. And what I'm thinking of is, verification problems, right? Which is one of the main applications of SAT, and therefore also kind of CSP type solving technology, right? Very often you actually have sort of minor variations of the same underlying hardware or software structure about which you want to verify. And so you would assume that these might not be identical graphs, but if they're not identical, they might be very, very closely related. And so there might be another kind of real-world application.
That's actually a great point. So you wouldn't have to do all the work to verify from scratch, but you can...
That's it. And my understanding is, and actually, where is he? We have somebody here who's an expert on this, but in real-world verification, at least of software, what really happens is that you have to solve millions and millions of instances that structurally resemble each other, to the point where it makes sense to tune your solver, an existing solver, to handle them more effectively. Now, your approach is very different, right? You would say if they're correlated enough, we might be able to take a look at all of them together and solve them all in one go. And I think that would be much, much stronger.
Right. So in fact, I think that's the only main takeaway, that it leads to very different algorithms. I mean, the algorithm that we did here has nothing to do with dynamic programming, and the CSP has nothing to do with SAT solvers. Yeah.
What this might be like, there is, like you have several related programs, and they all have the same bug, right? You have the same.
And you're looking for the bug. That's the solution. Yeah.
That's where it comes from, right? Yeah. And then, but you have these closely related hardware, but they all have the same bug, and so it makes it maybe easier to find the bugs.
But I think the model of the clauses, right? I mean, in verification, it's very different. Yes. How that's translated into clauses is not.
No, he's not saying this particular algorithm. It's just
conceptually.
They have the same solution. You have different instances of the same.
I guess other settings where correlated instances, like any of these Bayesian optimization kinds of calculations, very closely related. You make a little change and it's like. very closely related instance.
Yep.
Just at a conceptual level.
No, the conceptual level, but this whole, I think the conceptual level here is not so divorced from actually trying to get your hands dirty and for specific problems, yeah. Okay, thanks.
Thanks.